In this video, we're going to look at how to graph all 6 trig functions. And to begin with, I always start with sine and cosine because a lot of the other functions hinge around the characteristics of sine and cosine in terms of the way we would graph them. Now, when it comes to graphing sine and cosine, we want to find our vertical features and our horizontal features, so that way graphically we can create a vertical and horizontal scale, so that way we can see one full period of the wave. Now, vertically, our vertical features are the amplitude and the midline. Now, the midline, like its name, represents the middle value of y for the trig function. So, and it's also known as the average value of the sine or the cosine wave. And sometimes it's referred to that in the applications. So the midline is exactly halfway between the maximum and the minimum. So midline is halfway between the max and the min. So algebraically, I could say it's 1/2 times max plus min. That'll work. So I have a max at this function at 1, a minimum at -1, so my midline is right in the middle there. Be my midline. Now, amplitude is the maximum displacement of the sine or the cosine wave from its middle value. So amplitude would be how far in any one direction do you go to get to a peak. So midline to max or midline to minimum is going to be my amplitude. So I could think of a way to get amplitude would be maximum minus midline. Or I could do midline minus minimum. And I could even find the distance from max to minimum vertically. So max minus min and half that. That would give me my amplitude as well. So there's some ways to get our midline. So amplitude, midline are our key vertical features. Now, something to keep in mind is that amplitude is always positive. I can never have negative amplitude. I mean, I can negate the trig function, but the amplitude is still positive. Now, our vertical feature is really just period. So, or excuse me, not vertical. Our horizontal feature is the period of the wave. Now, by definition, the period is how long does it take the sine or the cosine wave to complete one full cycle. Well, one full cycle, I can determine that a number of ways. For instance, if I'm looking at the wave we have graphed, if I start here at the origin, I can go up to the max, and I'm going to keep going until I have done everything that the sine wave is going to do, and then it'll start repeating itself. Once I get to 2 pi, if I go any farther, I have done everything the wave is going to do. And if I look, in terms of critical points of sine and cosine waves are maxes, minimums, and midlines. One full period is 3 midlines. So one full period is 3 midlines. Another way to find the period, let me change colors up here, and we'll go with this. Another way to find period would be, well, if I started at a max and I went along the trig function, so I went midline, minimum, midline, and got all the way back up here to this maximum that comes behind it. If I go any farther, I repeat myself again. So another way to find the period is the amount of space along the horizontal to go between 2 identical peaks. So max to max or min to minimum. And there's, based on the information, I could come up with some others. distance from maximum to minimum times 2, or 2 consecutive midlines doubled. There's a number of ways. But in a nutshell, that's our vertical features and our horizontal feature, which is period. Now, period, one other thing, is just like amplitude, period is always positive. Now, when it comes to graphing our trig functions, we want to make this vertical and horizontal scale, and I just made out a long list of things to this is kind of the process that you go through in order to graph it. I don't necessarily have to fill all these things out in order to do it, but it makes it very helpful. So the first problem here on the left-hand side, I'm looking at trying to graph 3 times sine of 2 times x minus pi over 4 plus 1. I go find my amplitude first. My amplitude is 3. And then I want to go find my midline. My midline here is going to be positive 1. Now, my maximum y value. The maximum y value is going to be your midline plus your amplitude. So the maximum y that this trig function is going to have is 4. The minimum y value produced by this function, I take the midline and I subtract the amplitude from it. So 1 minus 3 makes negative 2. So now I know the range of the trig function, so I can set my vertical scale. The range is going to go from negative 2 to positive 4. So all of that is my vertical features. So I'm going to come down here. The way I graph these trig functions is I make scales. I'm going to make a vertical scale here. All right, so in my vertical scale, we have our range that goes from negative 2 to 4. So I'm going to go from negative 2 to 4. So that way I have my minimum, my maximum, and in between there I want my midline. So my midline was 1. All right, and now we're going to work at making our horizontal scale. To start with, we need to find our period. So the period of our trig functions, now we're talking about sine and cosine. Sine and cosine around our unit circle have a period of 2 pi radians. Now, to find our period, what we're going to do is we're going to start with 2 pi. And we're going to divide it by the number that multiplies to x. So in this case, it'd be 2 pi over 2. That's your horizontal stretch or shrink factor. So remember your transformations, if I multiply x by a value that's bigger than 1, I'm actually compressing the graph. And so the period of this wave is pi radians. So from start to finish, that's going to be pi radians. Now, I like to quarter my period when it comes to finding my critical points. And so a quarter of pi makes pi over 4. Now, before I go any further, let's talk about the why are we quartering the period. Let me come up here back to our original graph of a sine wave. One full period we have here in blue. That goes from 0 radians to 2 pi radians. 3 consecutive midlines made a full period. So this is one full period here. Now, I want to look and see how far apart are all of my critical points. Now, my critical points, I have 1 here at pi over 2. I have 1 here at pi. I have 1 minimum there at 3 pi over 2. And then my other one is right there at the end at 2 pi. So every pi over 2, I have another critical number. Well, pi over 2 is 1/4 of 2 pi. So that's why we're quartering our period. It's the amount of space in between, along the x, between our critical numbers. So every pi over 4 radians, I'm going to have a critical number. Now, our phase shift, sine wants to start at the origin. It wants to start at x equals 0, but I am transforming that graph here. So what I'm going to do is I'm going to take the inner function with x, and you can set it equal to 0, and that gives me x equals pi over 4. Pi over 4 is the first number that goes on my x-axis. Now, and also, that means I move this graph to the right in context of comparing it to the origin. So pi over 4 is the first number that goes on my horizontal scale. And then I'm going to continue on until I make one full period. Now remember, the gap between all of our critical numbers is pi over 4. And it takes 5 numbers, 5 critical points to make a period. So I go pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4. All right. Now from here, I like to take my midline and make a little dotted horizontal line. So that way it helps me and it helps you when it comes to graphing. Sine, let's make sure we didn't do any reflections. Nope, it's positive coefficient out front. Sine starts at its midline. So at pi over 4, I have a midline. When sine is positive, it goes from midline to maximum. So it goes midline to max, to midline, to minimum, back to a midline. And then I would just connect the dots and I'd have my one full period of this sine wave. All right, so there's the graph of sine. All right, I'm going to go to a new problem here, and I'm going to go to this cosine one. So I'm going to skip around and go to right here. Now, I want to graph it, so I need to find my vertical and my horizontal scale again. So I start with the vertical part, because that goes a little quicker. I want to find my amplitude. Well, the amplitude here is 3. Remember, amplitude can never be negative. So my amplitude is 3. My midline here is -4. My maximum y, remember to find the max y, you take your midline and you apply your amplitude to it by addition. So midline plus amplitude gives me -1. Now I want to find my minimum y, which would be midline minus amplitude, which gives me to -7. So my range goes from minimum to maximum. So the smallest number is -7. The biggest y number that's going to be outputted is -1. I have the vertical scale for this cosine function. So I'm going to go ahead and make that. So my vertical scale here goes from -7 to -1. And we have a midline at -4. So from here, we're going to now make our horizontal scale. So horizontal scale, we got to start by finding our period. Well, the period of cosine, just plain cosine, is 2 pi. To find my new period, I'm going to take the number that multiplies to the x, which in this case is pi over 6. And I'm going to divide 2 pi by it. So 2 pi divided by pi over 6. You do skip, change, flip, 12 units. So start to finish, it takes 12 units for this graph to do one full cycle. Like the previous example, every critical point is going to be 1/4 of the period away from one another. So I'm going to quarter that, and so every 3 units we're going to have a critical number. I just now have to get the first number that's going on my x-axis, or my horizontal scale. I find my phase shift. I'm going to take what's inside of the parentheses here of the function. I'm going to set it equal to 0. So pi over 6x minus pi over 3 is equal to 0. Let me double check that's correct. Yep. And I'm going to solve for x. So I add the pi over 3 to the other side, and then I'm going to multiply by 6 over pi, and I get 2. So 2 is the first number that's going on my horizontal scale, and again, this graph moved to the right 2 units. If I ended up with a negative number, that first point I put to the left of 0, which means it would have gone left. So the first number on my horizontal scale is 2. Now it takes 5 numbers, 5 critical points to make a full period. My next number, I'm going to add a quarter of my period to get the other numbers. So I go 2, add 3 gives me 5, add 3 gives me 8, add 3 gives me 11, add 3 gives me 14. So I have my horizontal scale. Now I want to try to graph this cosine function. I'm going to make a dashed line for my midline. Now, cosine starts at a maximum. Now, how do I know cosine starts at a max? Because cosine of 0 is positive 1. Positive 1 is the biggest number along the unit circle. So cosine wants to start at its max. However, I did an x-axis reflection by making it negative out front, which means in terms of trig functions, you're going to reflect them not over the x-axis, but you're going to reflect them over their midlines. So cosine, which wanted to have a max as its first value, now has a minimum. So the max becomes a min when I do the flip. If cosine was positive out front, it starts at a max. In fact, it's negative. I flipped it over its midline. And so we have minimum. The next number would be a critical point for its midline. And then we go to a maximum, and then a midline, and then a minimum. All right, and then I do my best to sketch it. Remember, the trig function is going to continue on forever in both directions. So one period of the cosine wave would look like that. Now, let's change gears and let's talk about our other trig function. So we want to talk about the graph of secant, cosecant, and tangent and cotangent. So to start with, I've given us the graph of sine and cosine. All right, I'm going to work here on the left. So I want to create a graph of y equals cosecant. Cosecant is the reciprocal of sine. So everywhere that sine equals 0, cosecant's going to be undefined, which means vertical asymptotes. So at all of the whole pi's here, where sine would equal 0, cosecant's going to be undefined. So I'm going to put vertical asymptotes. So at negative 2 pi, negative pi, at 0, pi, and 2 pi, cosecant's undefined. Now, because cosecant is the reciprocal of sine, everywhere that sine equals 1, which is its maximums, cosecant's going to have the same value because the reciprocal of 1 is 1. So at negative 3 pi over 2, I'm going to put a value at 1. So cosecant has a y value of 1. And at positive pi over 2, it has a y value of 1. Cosecant's also going to equal negative 1, where sine equals negative 1, because the reciprocal of negative 1 is still negative 1. So at 3 pi over 2, cosecant equals negative 1. And at negative pi over 2, cosecant equals negative 1. Now, I don't know if you've noticed this, but if I look here at the wave, I can kind of picture the sine wave in here. Now, you don't have to graph this, but I do when I graph cosecant, because it's a lot easier for me to graph sine than it is to graph cosecant. Now, here's the thing about the cosecant function. Cosecant will only share those values with sine and cosine. cosecant never equals 0. So if I start at negative 3 pi over 2, it also has to display unbounded behavior as it approaches an asymptote. So it's going to bend, it's going to go away, it's going to turn in the other direction from sine. So it's going to make a bunch of U's and N's, I guess you could say. So that's how I would graph cosecant. Now secant, I would do kind of the same thing. Secant is the reciprocal of cosine. So everywhere that cosine equals 0, secant's going to be undefined. So secant's going to be undefined on all the pi over 2's. So I'm going to make vertical asymptotes at all the pi over 2's. Like sine and cosecant, cosine and secant, they share peaks together. So where cosine equaled 1 or negative 1, secant will do the same. So at all the whole pi's, they're going to share those points. Now, you should see here that essentially what is going on is everywhere that cosine intersects its midline, secant has that vertical asymptote there. Now to finish graphing secant, I don't need that graph of cosine to make the graph of secant. It's just there as a visual reference, but secant has to display unbounded behavior, and it does not equal 0 anywhere, so it's going to turn away from cosine. It's going to turn away from the midline. And it also makes similar looking graph to cosecant. It makes U's and N's. They are sister functions, so I can make one become the other with a transformation. All right, so that's how I graph, or what the graph of secant and cosecant look like. Now let's go on to looking at the graph of tangent and cotangent. So remember, both tangent and cotangent functions are the quotient functions of sine and cosine. So I'll start with tangent. Tangent of x is sine divided by cosine. Now, I start this thing by thinking, all right, where is tangent going to be undefined? Tangent is going to be undefined everywhere cosine equals 0. So everywhere cosine equals 0, tangent is going to have a vertical asymptote. Well, the cosine wave is in blue, so cosine equals 0 at negative pi over 2 and positive pi over 2. So at negative pi over 2, vertical asymptote, and positive pi over 2. Now my graphs are different scales here, so actually I can go ahead and make one here at negative 3 pi over 2. So all the pi over 2's cosine equals 0. Now, because it's the quotient function, everywhere that sine equals 0, tangent's also going to equal 0. So sine equals 0 on all the whole pi's. So at all the whole pi's, tangent is going to equal 0. And now I want to go through and I want to sketch the behavior of tangent. Now, tangent is the quotient of sine and cosine. At pi over 4, tangent equals 1 because sine and cosine equal the same value. So at pi over 4, I'm going to have to kind of eyeball about where that is. Tangent's going to equal 1. At negative pi over 4, they, remember on your unit circle, sine and cosine have the same values, but one's positive, one's negative, which would make a negative value for tangent. So at negative pi over 4, tangent is negative. And I'd say, all right, well, let's keep going and get more data points here. And say, all right, well, they equal the same thing. The lines intersect again at negative 3 pi over 4, which would make positive 1. So negative 3 pi over 4, I got positive 1. And positive 3 pi over 4, sine and cosine have the same value but opposite signs, so that'd be negative 1. So 3 pi over 4 would be negative 1. So I have some points here. I'm trying to figure out, well, what will tangent look like? Well, tangent has to display unbounded behavior as it approaches its vertical asymptote. So I'm going to start at the origin, and I'm going to head towards pi over 2. So it's going to go through pi over 4, and then it's got to show that unbounded behavior. And then through the origin, working my way back to negative pi over 2, it has to go through that point pi over 4, negative 1, and then show that unbounded behavior by decreasing. And then if I look at the dots that I continue to have, and I say, okay, well, go from negative pi to negative 3 pi over 4. It's going to do this. And go from pi, work my way back to pi over 2. It's going to do this. Now, these tangent graphs continue going on forever in both directions. So in fact, I could continue this graph, and it makes a bunch of identical, I have a bunch of identical windows here of tangent within the intervals. All right, and then we have cotangent. It's the last one of our 6. It's kind of the same process. I start by thinking about where is it undefined. Tangent is, or cotangent is undefined everywhere that sine equals 0, because sine is in the denominator. So everywhere the sine wave equals 0, which is sine equals 0 on all the whole pi's, cotangent is undefined. And cotangent is going to equal 0 everywhere that cosine equals 0. So cosine equals 0 on all the half pi's. And then, now I start looking to try to get some points. And so I'm going to come back up here to the graphs and say, okay, well, let's try to make points for what's going on. At pi over 4, cotangent equals 1. Okay, well, just like tangent, pi over 4, cotangent equals 1. And at 3 pi over 4, I have sine and cosine have the same numbers but opposite signs, so that would be negative 1. And let's go ahead and sketch this window here and say, all right, well, from 0 to pi, if I'm sketching, as I work my way from pi over 2 back to 0, I have to go through pi over 4, 1, and then display that unbounded behavior. And from pi over 2 to 3 pi over 4, I have to go be negative 1, and then continue on to show that unbounded behavior. And I have my viewing window of what cotangent looks like, and I can continue this graph on. And say, well, you tell me how many periods you want to see. And I think I got to talk about that in a second. Talk about the periods of these trig functions now that we have graphs. So here's the graph. That's the graph of cotangent. Now let me go back to cosecant and secant. We know that sine and cosine have a period of 2 pi radians. Looking at the graph of cosecant and secant himself, you try to look and say, well, how many radians do I have to go for the graph to complete one full cycle? Well, if I start at 0 and I go from 0, I made a U, I made an N, and I go to 2 pi. If I go any farther, I'm going to repeat everything that I did, which means that the period of cosecant is also 2 pi radians. Now let's look at the same thing for secant. So I'll just pick an asymptote to start with. I'll start at negative pi over 2. Made my u, made the n, got back to the asymptote. If I go any farther, I'm going to repeat what I did. Well, one full period of secant, they go from 3 pi over 2 to negative pi over 2, is also 2 pi. So secant, cosecant, sine and cosine all have periods of 2 pi's. Well, let's look at tangent and cotangent. Tangent, if I look between, it repeats itself in between every vertical asymptote, and it looks identical. So its period is going to be the distance inside of one of those windows where it goes from negative to positive infinity, which is actually the distance from negative pi over 2 to positive pi over 2 is pi radians. So the period is pi. Now also notice this. Tangent goes, when I go a quarter of the period, so right here, whatever the vertical stretch is, the number that multiplies to the trig function, gets applied. So when I go, the coefficient of tangent is 1. When I go a quarter of my period, I get to apply that. And so that's going to help me get those other points. And the same thing, and I have a typo here. Why did it say tangent? It's supposed to graph cotangent. All right, so that needs to be cotangent x. So cotangent has a period also of pi radians. All right, so now let's start graphing. And I'm going to pick just a couple of these to do on this video here. All right, let's start with the one here in the top left. Now, here's the way I graph these. For secant and cosecant, I come through and I try to make the graph of either sine or cosine. So secant is the reciprocal of cosine. All right, and then so I'm going to make that graph. So the amplitude of cosine, secant and cosecant, they don't have amplitudes, and we don't necessarily refer to anything as their midline. So all this amplitude midline stuff is for the cosine function. So amplitude is 3, midline is -1. So I can get my max y would be midline plus amplitude is 2, minimum y, midline minus amplitude -4. So I have a vertical scale right now. So I'm going to go ahead and make that. So green is going to be my secant stuff. So I have my vertical scale, note this, for cosine. So I have to allow more room for the graph secant. So I have a midline at -1 for sine, or excuse me, cosine. I have a max y at 2 for cosine, and I have a minimum y at -4. Again, I'm leaving myself room. Now I have to make my horizontal scale. Well, the horizontal scale here for cosine, I find my period, which would be 2 pi divided by the number that multiplies to the input. So period is 4 pi radians. So when I quarter that, I know that every critical number is going to happen after pi radians. Now I want to find my starting point, or the phase shift. I'll set the inside equal to 0, solve for theta. That gives me -pi/2. So the first number that's going on my horizontal scale is going to be -pi/2. So negative pi over 2 is the first number, and it takes 5 to make a full period. And every number on our horizontal scale is going to be pi radians away from the number in front of it. So I'm adding pi every time. So my second number on this would be pi over 2, and then 3 pi over 2, 5 pi over 2, 7 pi over 2. And I'm going to graph this cosine wave. So I'm going to make my midline. Now its cosine is positive out front, so cosine wants to start at a max. Go max, midline, minimum, midline, maximum. And here's my cosine wave. Now, we didn't want to necessarily graph cosine, we want to graph secant. Remember, secant is undefined everywhere cosine has its midline. So I'm going to put vertical asymptotes where cosine has its midline. Secant and cosine share peaks. And secant will not cross cosine's midline, so I can sketch it. So in green is the graph of secant. All right, let's go to the next one here. I want to graph negative 2 cosecant of 2 theta plus pi over 4 minus 2. Well, just like I did for secant, I'm going to look at graphing negative 2 sine of 2 theta plus pi over 4 minus 2. And so I'm going to go find all my vertical features. So amplitude is 2. Midline is negative 2. So I can get my max y, 0. This is for sine, not for cosecant. The minimum y is negative 4. So I can go ahead and make the cosecant be green. The vertical scale for sine, which is going to be different for cosecant, but at least gives me a good starting point. So 0, negative 2, negative 4 is my vertical scale. For sine, again, I leave myself room because cosecant is going to have unbounded behavior. Now, if I was continuing the process of graphing sine, I would need to find the period, which would be 2 pi divided by the number that multiplies to the input, so 2 pi over 2, so pi radians. So start to finish is going to be a gap of pi radians. Every critical point that we graph is going to be a quarter of the period away from the one before it. So it's going to happen every pi over 4 radians. Lastly, we need to find the phase shift so we can put the first point on our graph. So I'm going to set the inside equal to 0, and I'm going to solve for theta. I do that, the first number that goes on my horizontal scale is going to be negative pi over 8. So negative pi over 8 is the first number that I'm going to put here on my horizontal scale. And it's going to take 5 critical points, to make a full period. Now to get the next numbers that are going on there, I'm going to add a quarter of my period every time. So I'm adding 1/4, which is 2/8. So next will be pi over 8, then 3 pi over 8, then 5 pi over 8, then 7 pi over 8. And I'm going to graph this cosine wave. So I'm going to make my midline, or not cosine, what is it? Sine wave. Now, because sine is negative out front, How that changes the behavior of sine is sine still starts at its midline, but instead of going up to its maximum, it's going to go down to a minimum because it has to reflect over its midline value. And so I get my wave here for sine. So this is the graph of what that sine function would be. Now, cosecant, everywhere sine intersects its midline, cosecant is undefined. So I have vertical asymptotes here. Everywhere that sine has its maximum or its minimum, cosecant will have the same thing. And then I graph it. Cosecant and sine are going to turn away from one another. Cosecant's not going to intersect sine's midline. So in green is the graph of cosecant. All right, two more. Now let's look at graphing a cotangent function and a process to go through that. To graph the cotangent and tangent, I don't graph sine and cosine and make their waves. What I do is I find the vertical features, vertical part, the +2 on the end. That is where tangent and cotangent, what would be called the midline for sine and cosine, is the location of the points of inflections. So I say points of inflections are going to happen at y = 2. And I'm going to apply the vertical stretch. So when I apply the vertical stretch, I have to go 1/4 of my period. Now from this number of 2, I'm going to put 2 other values on my vertical scale. I'm going to put, so I have 2. I'm going to add the 3 to it, make 5. And I'm going to subtract the 3 from it and make -1. Now technically, tangent and cotangent, they don't have amplitude, because amplitude is maximum displacement from the middle to a peak. Well, tangent and cotangent both increase to positive and negative infinity. So I can't call the 3 my amplitude. But I just refer to it as a vertical stretch factor. Now, my horizontal scale, on the other hand, I can do things similar to what we did before. I can find my period. Now, the period of tangent and cotangent functions themselves is just pi. However, I'm applying a horizontal stretch by multiplying the input by 2, so I got to divide pi by 2, and there's my period. So start to finish, this one period we're going to make for cotangent is pi over 2 radians. I want to quarter my period because just like I do for all the other trig functions. So pi over 8. And now I want to find my starting number, my starting value for x, my phase shift. I'm going to set the inside equal to 0. Solve for theta. Pi over 12. So pi over 12 is the first number that goes on my horizontal scale. Now, if you want, we can take and where those points of inflections are going to go, we can make a dotted line there to kind of help us out. Now, we want to get a full period. Now, full period, let's make our 5 marks on our x-axis. Now, to get to the next number that's going on the x-axis, we have to take pi over 12, and we have to add pi over 8 to it. I do that, and I get 5 pi over 24. And then I'm going to keep adding pi over 8 until I get all of my numbers. So we'd have, the next would be pi over 3. And the next one would be 11 pi over 24. And then we'd have 7 pi over 12. Okay, so now we have to go through the process of, all right, we need to graph this cotangent wave. And I need to think, all right, well, what does cotangent start at?
Debbie Tillett or any custodian, please come up to the main office.
Cotangent of 0 is how I determine what kind of point I start at. See, cotangent is cosine over sine. Sine of 0 is 0. So cotangent actually, cotangent of 0 is undefined. So the first number on this graph is going to be a vertical asymptote. Now, from here, now start to finish for this, if I start with a vertical asymptote, I'm going to end with a vertical asymptote for cotangent. And halfway in between those vertical asymptotes, I'm going to have my point of inflection. So I have that. Now, cotangent, remember, off our original example, cotangent is a decreasing function unless I reflect it. So I have a positive coefficient, so it's going to continue to decrease. So when I go from pi over 3 to 11 pi over 24, I'm going to be going down to, I'm going to be at -1. Here, when you go a quarter of the period from the midline in any direction, you apply your vertical stretch. And now we sketch. So it's, as I work my way from pi over 3 to pi over 12, it's going to go through that point we made at 5, and then it's going to start to show unbounded behavior. And when I go from pi over 3 to 7 pi over 12, it's going to go through that point we made and also display unbounded behavior. So the graph of cotangent would look something like that. All right, one more example, we'll do tangent. And it'll be negative out front. So the process to graphing tangent, again, like cotangent, I am not going to graph sine and cosine and look for their intersections and then graph from there. All right, I'm going to make my vertical scale. Now this 2 is where my points of inflections are going to be. So that's going to happen at y equals 2. My vertical stretch or shrink factor is 1/2. So the numbers I'm going to put on my vertical axis here I'm going to put 2, 2.5, and 1.5. Now I want my horizontal scale. Well, I got to find my period. The period of tangent should be pi. However, by me multiplying the input variable by 2, I need to divide pi by that number, so my period is pi over 2. And to plot all of our points, we're going to quarter our period, which is going to make pi over 8 radians. So every mark on my x-axis is going to be pi over 8 radians from the one before it. To find the first number, we got to find our phase shift. So I'm going to set the inside equal to 0, solve for theta. I get pi over 4. So pi over 4 is the first number that goes on my horizontal scale here. So pi over 4. And we're going to put 5 numbers like we do for the other ones. Now to get the next number, we're going to add a quarter of our period to the pi over 4 to get to our next one. So pi over 4 plus pi over 8 makes 3 pi over 8. Add another pi over 8, makes pi over 2. Add another pi over 8, 5 pi over 8. Add another one, 6 pi over 8. So I have my horizontal scale and my vertical numbers I'm going to use. Now, we can make our dashed line for our points of inflections to go on. And now I got to figure out, all right, well, what do I start with here at pi over 4? Well, to answer that question, you ask yourself, what is tangent of 0? Tangent of 0 is 0. So tangent starts at a point of inflection. So if it starts at a point of inflection, we're graphing one full period. That's from start to finish. You're going to identical points. That means I'm ending at a point of inflection. And halfway in between the points of inflections, we have our vertical asymptote. So I'm going to put a vertical asymptote here in the middle. So I just have to sketch the behavior from here. Well, tangent is supposed to be an increasing function. However, I am multiplying tangent by a negative 1/2. What that means is I reflect it over this so-called midline that we drew. I flip it over, so instead of increasing, it's going to be decreasing. So at 3 pi over 8, I'm going to have a value at 1.5. So that way, when I go from pi over 4 to 3 pi over 8, I show that I'm going to be decreasing. Now, if I was to work my way to the left of pi over 4, I'd be going up. At 5 pi over 8, so I can ensure that I stay decreasing, 5 pi over 8 is going to have a y value of 2.5. And so that way, as I work my way from left to right, I'm going to see it's decreasing.